Now it becomes interesting. On the D wave 2x adiabatic quantum computer. So I hope I got it almost right. You can probably repeat it.
Well, that was perfectly right.
Okay, so we'll see what this is all about. I'm looking forward to that. So go ahead again.
Thank you.
And don't forget the water.
All right, not sure that I have to present myself again. My name is Daniel. Yes, the title, Multiple Query Optimization on D-Wave 2x Adiabatic Quantum Computer. So in the last talk, I have actually shown how to exploit a hardware platform that we are heavily using today. And in this talk, it's about how to exploit a hardware platform that we might use in the future. The motivation for this work is the following. I think the first keynote on this conference referred to that. We have exponential data growth. On the other side, it has become more difficult to improve conventional computers since we already have the end of Banach scaling, which gave us exponential increase in energy efficiency, and Moore's law is ending as well. So this motivates us to consider new computing technologies in order to complement classical computers in the medium and long term. And one candidate that, let's say, has shown some promise, that is quantum computing. Now, in order to give a very simplified definition about what quantum computing is, we can say that quantum computers operate on qubits while classical computers operate on bits. And the difference between qubits and bits is that a qubit can be in two states at the same time that would be considered mutually exclusive according to the laws of classical physics, but they are allowed according to the laws of quantum physics. So this means that qubits can be 1 and 0 at the same time. So a quantum computer can be in multiple states at the same time. And with a highly simplifying intuition, we can say that this allows a certain parallelism that is not possible on classical computers. Now, you might have heard recently, a couple of weeks ago, that Google published a paper where they made experiments on a machine with 10 qubits. Quantum computing has, of course, until quite recently been a purely theoretical direction of computer science. But nowadays, there are some first machines that implement a limited form of quantum computing techniques. In this picture, we see the machine that I was using for this paper. The machine was also paid for by Google, but it was produced by the Canadian company eBay and is currently hosted at NASA Ames Research Center in California. If you would open up that machine, then you see qubits connected pairwise via couplings, which allows them to exchange information, and the connections between qubits are actually quite sparse. They are connected in the so-called chimera graph structure. And more precisely, those qubits are realized via tiny circuits made out of the metal niobium, which has the property that if you cool it down to a temperature of around 50 millikelvin, which is colder than interstellar space, then it becomes superconducting and power can flow into both directions at the same time, basically. And since power flowing into one direction represents a 1 and power flowing into the other direction represents a 0, it means that you can represent qubit superposition. Now I'm explaining the hardware to you because it defines the types of problems that we can solve on the machine. Because qubits can represent binary variables, and here we are connecting pairs of qubits, so we can represent quadratic formulas which depend on binary variables. And the machine translates the values of those formulas into energy levels, and it executes a physical process that will aim at finding the minimum energy state, which is at the same time which represents the minimum value of the formula. So this is a machine for minimizing quadratic formulas in binary variables, which is an NP-hard optimization problem called quadratic unconstrained binary optimization, short QUB. Now, this machine has been controversially discussed over the past years, and here I have collected a couple of comments from some of the most famous scientists in the area of quantum computing. Well, The first topic that the discussion centered on is whether the machine actually serves the tech quantum computer, whether those quantum effects actually play a significant enough role during the computation. And since quite recently there is actually a consensus between the guys here that the machine actually serves the tech quantum computer, even though it only realizes a very limited form of quantum computing. So now the attention is currently shifting to the question of, okay, let's assume we have some limited form of quantum computing. Is this actually helpful? Will this improve things compared to classical computers over the long term? And one question that is raised by several of those and other researchers in that area is, how well can the machine perform for practically relevant problems that do not comply with the natively supported input format? Because if I want to use that machine for optimization problems in the database domain, for instance, then usually I first have to transform them into a quadratic formula to minimize. And this transformation leads to a huge overhead. So this paper here contributes a little bit to that discussion because we have shown how to solve a classical optimization problem in the database area on that machine. And this classical problem is multiple query optimization, also called multi-query optimization, where you basically want to minimize execution time for a batch of queries. So initially, we assume that we are given a batch of queries, and for each of those queries, we are given a set of alternative query plans. In those plans, they can share intermediate results, and if you do that, then you can reduce accumulated execution time. So the question becomes, how can I select the optimal combination of plans? Now the transformation function, which I will discuss in more detail in the following, operates in two steps. In the first step, we have to transform an instance of the multi-query optimization problem into a quadratic formula in binary variables to minimize, because this is the format supported by the machine. I'm going to give you more details on the transformation step in the following. But once we have a quadratic formula, we are actually not done with the transformation yet. Because in a second step called embedding, we still have to decide which qubits represent which variables in that formula. So we have to assign variables in that formula to groups of qubits that will represent them. And this assignment is actually subject to various constraints that I'm going to discuss in more detail in the following. So finding a good embedding is actually a highly non-trivial problem. Concerning the first step of the transformation, we want to transform an instance of the multi-query optimization problem into a quadratic formula. And this formula will use binary variables that represent whether or not specific plans are executed. And now I can partition the terms in that formula into three groups based on their semantics. First of all, I have terms in that formula which represent the objective function that I want to optimize. But then I have also terms in the formula which take very high values if problem constraints are violated. And since we are minimizing, this will motivate us to respect the problem constraints. And finally, I will have terms in the formula that are about consistency, which basically enforce that all qubits representing the same variable will be assigned to the same value. I can further partition those three terms into the following subterms. The objective function in our case is the execution cost for the entire batch of queries, which is the execution cost of the single plans we execute minus the cost savings by overlapping work between different plans. The problem constraints in our case is that we want to answer each query in our batch, so you have to select at least and at most one plan for each of the queries. And once I integrate those three different terms into the formula, I can actually multiply them by weights in order to express priorities between them. And then the first priority should be the consistency term, because all of the other terms are formulated under the assumption that I have consistent assignments. Now the second priority should be the constraint term, and the third priority should be the objective function, which basically means that you're optimizing the objective function among all solutions that are consistent and satisfy the problem constraints. Now, all of that translates into quadratic formulas. You find more details on that in the paper, and we also explain in detail how we can precisely calculate those scaling factors in order to express priorities. Now that is the first step of the transformation. In the second step, we need to assign each variable in that formula to a group of specific qubits in the annealer. Now, I have to pay attention to two things once I do those assignments. First of all qubits representing the same variable have to be connected via those couplings, because I want to be able to exchange information between them in order to make sure that all of them adopt the same value. The second thing I need to pay attention to, if two variables appear within a product in that quadratic formula, then their qubits have to be connected by at least one connection, because those couplings, they express quadratic products. In this example, I show how I can embed four variables that can appear in quadratic products together. Here the qubit color indicates the represented variable, and as you see, qubits representing the same variable are connected, and if you select any pair of variables, then you will find that their qubits have at least one connection between them. So this works for four variables, and I'm using two qubits to represent each of the variables. I can generalize the so-called triad pattern in order to represent higher numbers of variables that are all densely connected, like that. Up here, for instance, 16 variables. The problem is, however, that the number of qubits that I need to represent one variable keeps growing. So the number of qubits on the current machine is very limited. We have around 1 kiloqubit. So we want to be very efficient about how we use those qubits. And what I can do in order to represent more variables with those qubits is I partition the variables into densely connected clusters, while different clusters only have sparse connections between them. And as you see here, it allows me to represent more variables than before with the same or even less number of qubits. Now the question is, however, how can I decompose the problem variables of multi-query optimization in that way? In order to answer that question, I need to analyze the terms that appear in the quadratic formula. Let us do that. On the right side, each blue dot represents one variable, representing the execution of a specific plan for a specific query. Now we are analyzing the terms that I have in the quadratic formula and see which connections between variables they require. The execution cost of single plans does not introduce any connections between variables, while the term representing cost savings introduces connections between those plans that can share work between them. The selection of at least one plan doesn't introduce connections, but the constraint I can select at most one plan for each of the queries actually connects all variables representing plans for the same query. And based on that analysis, I can conclude that the right way of partitioning my variables is that I put together in the same cluster all variables representing alternative plans for the same query, and all variables that represent plans which belong to queries that can share many intermediate results. This is the transformation function. In the paper, we also formally analyze the quality of that transformation. First of all, we show that the transformation function can be calculated in polynomial time on a classical computer, but we're also interested in seeing how well does the output of the transformation map to the quantum annealer. How convenient is the output of the transformation for the quantum computer. And in particular, we're interested in how many qubits we require in the transformation, because the number of qubits is still very limited. And the number of qubits equals the sum of the number of qubits required to represent each single problem variable. And in the following, I'm going to show that we can also bound the number of qubits required to represent a single variable. We can do so as follows. We have seen before that products between variables are represented by couplings in the matrix. So if I count for each variable the number of products that it appears in the quadratic formula, it gives me a bound on the number of couplings that I need. And since the number of couplings per qubit is a constant, it at the same time gives me a lower bound on the number of qubits that I need, which grows linearly in the number of queries for constant cluster sizes, but quadratically in the number of plans. And later in the experiments, we will also see that indeed the number of queries that we can represent is much higher than the number of plans per query. Now, this analysis establishes a lower bound on the number of qubits required to represent the quadratic formula, so it actually only refers to the first part of the transformation. We also show a specific method that allows us to embed our problem, and by analyzing that second step of the transformation, we can establish an asymptotic upper bound in the number of qubits that we need. And by comparing the upper bound to the lower bound, we see that they asymptotically are equivalent, and we can conclude that the second step of our transformation is therefore asymptotically optimal. However, this still leaves open the possibility that we can find quadratic formulas which are more efficient about how they use the available qubits. Now, the focus of our experiments is first of all a proof of concept, and then a comparison between a classical computer and the quantum annealer. And that is actually a very tight race, because the quantum computer suffers from transformation overhead, while the classical computer can work directly on the original problem instances. And on the classical computer, we ran all those algorithms that are commonly used for multivariate optimization, such as genetic algorithms, hill climbing algorithms, quadratic and linear programming, also using linear programming for approximating the solution, while on the quantum annealer, we only run our approach, since it is so far the only one available. Now, we are comparing two fundamentally different technologies here. So you can imagine that the relative performance between them is quite sensitive to the structure of the input complex. So asking who wins is perhaps not a good question actually. Perhaps a better question is whether each of them can win for specific subclasses of test cases. And in case of the classical computer, the answer is actually immediately yes.
Because there are problem instances that can be solved conveniently on a classical computer, but we simply don't have enough qubits on the current annealer machine to represent them using our mapping. And the more interesting question is therefore whether there are also problem classes where the quantum annealer wins. And this is therefore the focus of our experiments, in which we want to find out
how much faster the quantum annealer is at finding approximately optimal solutions. We always compare against the best algorithm on the classical computer. We have run all those algorithms you have seen before on all of the test case instances. And we generated different test case classes that we classify on the x-axis according to how many qubits you need on average in order to represent a single problem variable. And as you see, you can get some significant speed ups if the number of qubits per variable is very close to the theoretical optimum of one. You have a factor of more than 18,000. However, once the number of qubits per variable increases, the speed up is quickly decreasing. Still, the answer to the second question is yes as well. And in summary, the motivation for this work was that we want to consider new computational paradigms to complement conventional computers in the medium and long term. We have shown how to solve multiple query optimization on that quantum annealer. In our experiments, we give a proof of concept and show that for some instances it can perform well. And I believe that this is the first experimental paper on quantum computing in the database community. Thank you very much for your attention, and I look forward to
thank you very much. Very fascinating.
Thank you.
Are there questions? Pardon?
Yes and no.
Yes and no. Go ahead. So I have a very simple question. I mean, we always look at our community and say we do this query optimization stuff, but behind it there are algorithms that are applicable in other areas as well. I mean, depth first search is not limited to our community. So when you envisage that other problems can use this approach to be solved in a similar way?
That's a very interesting question, actually.
I mean, I'm looking beyond our own community now.
Like this approach, yes. Well, I mean, in principle, of course, I mean, you can reduce all NP-hard problems to each other. However, in order to be efficient about how you use the available qubits, I believe it would have to be relatively similar problems, because I'm exploiting some...
Similar in structure, or?
Yes, similar in structure. Yes, very similar in structure, I would say. I mean, you can use it in principle, but in order to make it perform well, I think the problem really has to be very similar. In principle, you could use it, but in practice, probably it won't give you very good performance. It's quite tricky to actually get good performance. You really have to be very careful about how you use qubits and which connections you really need. So, yeah.
So how long did it take you to be clever about it?
Well, actually, I was working on this already for a couple of years, but it took me a long time to get access to one of those machines. So yes, a couple of years ago, I was working this, like not exclusively, of course, but there's over a longer period.
There's a question from the auditorium. Go ahead. Can you identify yourself?
I'm Spirit from MSQL. How long does it take the D-Wave to solve a single instance of these problems, or does it vary? And is the speed up because the classical computer is faster or slower, or because the quantum computer is faster or slower?
Right. Actually, in the paper you find some very detailed experimental results. This was only the application. In the paper you see really for each test case instance what was the relative performance between different methods over time. So it depends on what quality you want, how long it takes to solve them. I mean, the quantum annealer usually executes multiple runs. One run takes less than a millisecond, so that is very fast indeed. However, the problem, probably in general in quantum computing, is that in order to sustain those quantum effects that you need to compute, you have to do a lot of shielding. If there is like any interaction with the outside world, then they will vanish. And actually the reason why the machine is so big, as you have seen, is that they use a lot of shielding. The whole circuit is actually very small, but it's put inside a vacuum, is cooled down to extreme temperatures and so on. So shielding is very important, and despite doing a lot in order to shield it, it will often not work, and you will have disturbances during the run. This is why in general you do multiple annealing runs. So one run is very quick, but usually if you want to be sure that you find a good solution, then you would want to do like 10 or 100 runs at least, right? So the question how long it takes, it depends on, you would usually fix the number of iterations that you want to perform.
Thank you.
Paul?
I'm going to ask you to speculate a little bit. The number of qubits that you need is quadratic in the number of planes. Typically we have a fairly large number of planes, so that's sort of problematic. Now the question really is, does that quadratic term depend in any way on the interconnect structure you have between the qubits? How many connections you have? Because the D-wave has a specific structure for how qubits are connected. If you have total freedom in how qubits are connected, can you get rid of that quadratic term or not?
If you have total freedom about how qubits are connected, then you can definitely get rid of that quadratic term. This is an artifact of having to represent one variable by many qubits in order to realize all required connections. However, I should perhaps say, I mean, this is like the first approach in order to map it. I think it might be possible that we can actually get rid of that quadratic term by still using, by still having the same connection structure.
All right.
Yeah.
Okay, thank you very much again for this first paper. So don't leave the room. We have another fourth paper, which is somehow the